So we left off previously saying many mechanisms are composed of multiple steps, and some steps are faster than others. Some steps have higher activation energies than others. Well, today we're going to use that knowledge to come up with the rate law for reactions. Remember, we previously said that the rate law for a reaction has to be determined experimentally or by mechanism. Today is the by mechanism day. So if we are given this reaction up top as the overall reaction, and we are told that that reaction takes place by this mechanism, this series of 3 elementary steps, we can come up with a rate law for the overall reaction. This top step is a very fast step. It's an equilibrium step. There's a forward and reverse that happen very quickly. So because we know all of these steps are elementary steps, we can write the rate law for each step individually. So if we take this first reaction here, we say the rate law for that forward reaction is the rate equals K1, because that's the specific rate constant for that reaction, K1 times the concentration of N2O5. Rate equals K1 times concentration of N2O5. Okay, cool. Because it's equilibrium and the reverse reaction is also happening, we need to consider the rate law for the reverse reaction as well. So the reverse reaction will be rate equals K negative 1 times the concentration of NO2 times the concentration of NO3. Note that when you know your steps are elementary steps, the coefficient in front of your reactant is the exponent in your rate law. That's not the case if your steps aren't elementary. So we can move on to the next reaction. The rate of that one is K2 times NO2, concentration of NO2, times the concentration of NO3. Check. The last one, the rate equals K3 times the concentration of NO times the concentration of N2O5. Okay, cool. We said the point of this problem is trying to come up with the rate law for the overall reaction without having to run experiments. Well, the rate of the overall reaction is all dependent on the slow step. The slow step is pumping the brakes, halting the reaction, keeping the reaction from going any faster. So the rate of the overall is all dependent on the rate of the slow step. So that makes us say that the overall reaction has the same rate law that the slow step does. However, there's a problem. Rate laws can never be written in terms of an intermediate because the concentration of an intermediate cannot be measured. So what do? You're going to have to take advantage of the definition of equilibrium, where we know the rate of the forward is equal to the rate of the reverse. Let's do that. So we saw the rate law for this guy was K2, NO2, NO3. But the problem was NO3 is an intermediate. It's something that's created in an early step and consumed in a later step, but does not appear anywhere in the overall reaction. Knowing that the rate of the forward is equal to the rate of the reverse for our equilibrium equation, we can say K1 times N2O5 is equal to K negative 1 times NO2 times NO3. Who was the problem child above? NO3. Because NO3 was the problem child, solve this equation for NO3 concentration. NO3 concentration is equal to K1 over K negative 1 times N2O5 divided by NO2. So since these two things are not intermediates, their concentration can be measured, so we can plug that back into our overall rate law up here. So this plugs in for our NO3 concentration. That makes our rate law for our overall become K2 times K1 divided by K negative 1 times NO2 times N2O5 divided by NO2. Well, okay, I can do some further simplification here. These are the same, so cancel it. This is a rate constant times a rate constant divided by a rate constant. I think I'm going to call that a constant. We'll call it K prime, not because it's important to call it K prime, but just because we want to identify that as a different K from all those other Ks. So the rate of the overall reaction will be K prime, that's these, times the concentration of N2O5. Yep. What was the big reason we had to do this? The rate law for the slow step included an intermediate in the rate law, and intermediate concentrations cannot be measured. So when talking about reactions, not all of them, we have said, are spontaneous. Not all of them form products. There are two main reasons why product may not be formed or not much product is formed. Either it's thermodynamically unfavorable, as in it gives you a positive delta G, and positive delta G is non-spontaneous, or it can be thermodynamically favorable, so it gives you a negative delta G, but the activation energy is so high, this activation barrier is so high that it's kinetically unfavorable. You can wait for a very long time and never get any product. So spontaneous according to delta G, yet no reaction actually happens over a long period of time. So in order to get some product in a reasonable amount of time, you need it to be thermodynamically favorable and kinetically favorable. You need it to have a negative delta G, and it needs to have a small enough activation barrier to overcome. One way that you can speed up reactions is by adding a catalyst. If a reaction has too high of an activation barrier, you can frequently add a catalyst that will lower the activation barrier. A catalyst is a substance that increases the rate of a reaction without itself being consumed. A catalyst makes the rate of the reaction faster because a catalyst lowers the activation energy. So if I follow this red trace, that's not very kinetically favorable. It may form some product, it may not, but it's not as kinetically favorable as the blue because the blue humps are lower. Note, a catalyst changes the mechanism of a reaction. It does not simply lower the activation barrier, it changes the mechanism of a reaction as well. Be aware of that. In this reaction up top, we have a catalyst. Who is the catalyst? A reaction has to be there in the beginning and not consumed, so it's there in the end as well. Is it IO minus? No, IO minus is an intermediate. Intermediate, created early, consumed later. Catalyst, there in the beginning and there again in the end. I minus is the catalyst. In the bottom reaction, is there an intermediate? Is there also a catalyst? The catalyst is hydroxide. The intermediate, NaNO2 minus. Two definitions we have to be aware of. Catalysts are actually seen all the time, every day in the real world when you think about enzymes. Enzymes are catalysts that expedite reactions happening in our bodies. If you look at our plot over here, if you're just waiting on S, the substrate, to become P, the products, without an enzyme, that activation barrier is probably way up here. The hump is probably way up there. But when you add an enzyme, aka a catalyst, to the mix, it changes the mechanism, first of all, so you have two humps instead of one, but it lowers the activation barrier so that a reaction can happen, and it can happen in an appreciable amount of time. It doesn't take forever. If it took forever, we would be in trouble because enzymes catalyze reactions in our bodies all the time, all day, every day. Cool stuff.